Hey all, the next thing that we're going to talk about is actually measuring the ocean. And there's really kind of a couple of things that we can measure. We just went through all of this information about how we measure air temperature, right, on the continents. And that's not super hard, right? Because you can stand there, right? You can set a thermometer down and you can walk away and you can come back and check it in a week and see what sort of data you've collected. The ocean, well, that's a little bit different. The first characteristic about the ocean, and really arguably the most important, is the temperature, right? And we call that the sea surface temperature. So sea surface temperature, well, right away we start to get into a problem, right? So what's the definition of the surface? And it turns out it's variable. Obviously we're not talking about the deep ocean. We're not talking about kind of the near deep ocean. We're talking about the surface. But again, that definition changes. We're going to see a little bit later. There's one fairly common method that we can use in the modern world that really measures the temperature, what we call the skin of the ocean, kind of the upper 1 millimeter. Well, that's going to be really variable. And it's going to change all the time. Generally, we can go a little bit deeper, and the definition of sea surface really ranges from about 1 millimeter to about 20 meters, or about 70 feet. And that depends on what sort of method we're using to measure that temperature. So sea surface temperature is really important. We know that the temperature of water can affect the air, right? Water has a much higher what we call heat capacity. And so, an isolated pocket of warm water, especially on a cold day, can cause increased evaporation. And in a place like near the Great Lakes, those aren't exactly the ocean, they're freshwater, but you can get what we call lake effect snow, right? So you get warmer water causing increased evaporation, increased precipitation in cold weather. The ocean can do the same thing. Also, sea surface temperature is really important. The difference between sea surface and air temperature, that's kind of the nuts and bolts of how hurricanes form, right? So what we call cyclonogenesis. A hurricane is just a special type of cyclone. Another thing that's really important to think about, and this is something we haven't talked about in quite a number of weeks, is this notion of thermohaline convection, right? So deep ocean currents and their driving forces. Well, the driver for a deep ocean current to downwell is essentially increased salinity by freezing, right? So as water freezes, just the freshwater portion does, salinity increases, that water drops. In other areas where the water's warmer, creates an upwelling current. So sea surface temperature can act a little bit like a throttle on how effectively those thermohaline currents move. Another thing that's a really big idea is the amount of heat or energy stored in the oceans at large, right? In a bulk sense. What's the quantified energy stored in the ocean basins? It's a really big number. And it's hard for us to measure temperatures, at every depth and every kind of position across the oceans. But sea surface temperature can really help us correlate that. And so we can, have some broad data. Maybe we can have a few point checks. So we can have some correlation that we can interpret what the ocean, what the volume of heat stored in the ocean is. So just as with temperature, there's some history here, right? So how did we start measuring sea surface temperature and how did we get to where we are now? Well, really the first kind of oceanographic characteristic measured was sea temperature. And famously, actually, Benjamin Franklin, as he was going back and forth between England and the United States, he would take a mercury thermometer and actually just dip the thermometer kind of in a raw sense down into the water, pull it back up, and mark a temperature. This was kind of foundational in understanding the Gulf Stream, right, which is one of these ocean currents that we've talked about that takes warm water from the kind of Florida region up to kind of northern Europe and England, and actually helps moderate the temperature there. Soon after that, we realized, it's not effective to take a thermometer and just stick it down in the ocean. It was much more effective to take a sample of the ocean and bring it up to the surface and then measure the temperature, right? There was a lot less, potential error in that case. And plus the thermometer wouldn't break, right? You've got instrument sensitivity. And so we actually had, really, starting 150 years ago, we had buckets. So there's kind of a standard wooden bucket with a metal weight on the bottom, and that bucket would be thrown overboard, dropped down, kind of sunk to some depth, and returned to the surface, and then the temperature would be measured. Obviously, a lot can go wrong there, but that was really the kind of name of the game for quite a long time. These wooden buckets had a couple of problems. They were superseded by canvas bags, which are a little bit better than wooden buckets in a sense. It's a canvas bag with kind of two wooden rings in the top, providing the bottom and the top. And the top was open with a little spring-loaded lid. So you could drop the bucket down, or the bag, would go down to the water. You got to the depth that you were hoping. You could kick that spring-loaded lid. It would close. It would take a sample of the water at that depth. You could bring it back up and, again, measure the temperature. So one of the things that becomes obviously apparent here is that there is what we call a cool bias, right? So you collect the temperature in situ at that location. That's, a fancy Latin term for meaning in place. And as you're bringing that bucket up and you get the thermometer out, you get out your book and you're doing your thing, that water is cooling off, right? So it actually is colder than it is when you sampled it, right? So we call that a cold bias. And actually, there's been a lot of research to measure how quickly temperature drops in canvas bags and wooden buckets. And that's actually allowed us to go back and use, 100 years of oceanographic data and hopefully have it correlate more closely with modern collected or modern kind of remotely sensed temperature data. So you can see this is an image that kind of comes out of one of those studies, right? This is a canvas bag, and you can see they filled it with warm water and then took thermal images at different intervals of time, and you can actually see it cool off, right? So it depends on how much time passes from sample collection to temperature measurement. So the next shift actually occurs with the motors or the engines of boats. That's my terrible drawing of a propeller. And so boats, we really started measuring temperature like this in the 1950s. Boats will bring water on and use that to cool the engine as the engine's plugging away, moving the boat across the ocean. And we actually keep track in the engine room the temperature of that incoming water and then the temperature of the engine. We've got a temperature gauge. It's similar to what we have in your car. And so this cooling water, we have accurate records of the temperature of the water brought into the ship to cool the engine. Now, that has a different problem, right? It actually has a warm bias because it's in an engine compartment, so the water's potentially warmer than it was when it was brought into the boat. And then additionally, not all boats are the same, right? We don't have a standard boat, a standard ship floating around. So larger ships are going to collect water at a different depth than smaller ships. So again, there's kind of a lot of moving parts here. As you can see, measuring sea surface temperature and coming up with an accurate record is not so simple. In addition to research vessels who are collecting in situ, in place measurements, we also actually have thousands of buoys that are floating around. They're kind of two different flavors. There's what we call moorings, those that are actually attached, anchored to the seafloor in some manner, and drifters, those that just kind of drift around the ocean. And those actually collect all sorts of information. Not all of them are the same, and there's lots of different styles run by different countries. Some are similar to a weather station. Some are just measuring essentially water temperature and depth. Some are these little kind of disc style ones. Others are a lot taller. Generally, they have a solar panel on them to kind of provide energy. They make these measurements, and those measurements are then sent to a satellite. So that's, the kind of ground observation of modern sea surface temperature. Remember I talked about this method of in situ measuring, which again is Latin for in place. So really in about the 1980s, we began measuring sea surface temperature essentially the same way that an infrared thermometer works. And in this case, we have satellites, and they are detecting the ocean. And as the ocean is operating at different temperatures, if you guys think back and remember the electromagnetic spectrum, they give off a very specific frequency of infrared radiation, and that frequency is correlated to temperature. So we've got armies of satellites that are kind of scanning the oceans, constantly measuring the sea surface temperature. And like I said, that data has really been available since the 1980s, so it doesn't go back really far, right? If we want to take our sea surface temperature and go back to the mid 1800s, we're actually going to have to compile lots of different types of data, right? Some of it's going to be from buckets, some of it's going to be from bags, some of it's going to be from ship intake, and some of it's going to be from buoys, and some of it's going to be from satellites. And actually, they kind of are all married in a really interesting way. So one of the problems with satellites that are collecting infrared data off of the oceans and measuring temperature, kind of again related to which frequency of infrared radiation is being given off, that's the instance where we just know the temperature of the skin, right? About the upper 1 millimeter. That's what we're measuring when we're using these kind of temperature sensing satellites. Now, like I said, that can change really often. If you have a windy day, there's like better mixing, so you don't get as much kind of spot heat locations. On a calm day, there tends to be some strange patterns that emerge. But actually, we have some pretty sophisticated computer algorithms and methods that actually take in situ measurements, right? So we have all this live data from our army of buoys floating around in the different ocean basins, and we can actually overlay the infrared data from satellites, and we can kind of jive the two, right? So that's what we call it's essentially providing a ground check and a calibration for that thin skin temperature as compared to temperature at 3 meters of depth, or something that's much more standardized. Okay, well, so that kind of talks us through our sea surface temperature measurements, buckets, bags. There's even like a special German scoop bucket, ships, buoys, and infrared satellites, right? That gets us to the modern era. The next thing that I wanted to talk about is actually sea level itself, right? This is something that comes up in the climate discussion often, and it's something that requires a very high level of precision. And so in the next video, we'll examine kind of how we look at sea level and how we define sea level. Okay, see you then.